Logic gates and special combinations. In this presentation, we're going to be looking at latches, flip-flops, and some flip-flop applications such as registers. Well, let's get going. A latch is a logic gate connection which latches or saves a signal after the signal has been applied. This saving of the signal is the premise of computer memory. If I were to push this push button down and apply a high signal to this OR gate, what we would see is that due to the connection from output to input here, while I have it pressed, the light comes on because the output is high, but when I remove my finger from the push button, voila, it remains high. Now it should be understood that the signal has been saved and that the logic gate has latched itself to save that signal which was provided by the push button. It should also be understood that this is only a basic partial example of a fully functional latch, as it cannot be reset back to its original state. Below is a full SR latch. The SR latch includes two logic gates with different types of connections from input to output. The SR represents the words set and reset. This is the most basic type of special combination logic gate. What you'll notice is that the outputs are always going to be opposite from one another. When this one is high, that one is low. And if this one's made high, then that one will be low. And the two inputs are often referred to as set and reset. Well, let's see how this works. I'm going to go over and press the set. And what you'll notice is that the lower light comes on, and it doesn't matter if I keep pressing the set, it doesn't change the output because it's been latched. If I want to reset it, I have to press the reset. And again, the reset's really operating in the same function. I can press it once and it resets it. Go back here, press it, and it stores a signal again in the opposite side. Press the reset again, and again we see the whole thing go back to its original state. So a set reset latch, or an SR latch, is simply a means of us storing a signal. Now, a signal is saved when it is applied to the set terminal, we can see up there. The outputs change, then remain, as in stay, even after removing the signal from the set terminal. The status of the memory circuit can be returned to original state by applying a signal to the reset terminal. Now, most input pilot devices rely on springs to return them to their original state after actuation. During the operation of a pilot device, the connection can be intermittent until full pressure is applied or released. This is known as spring bounce, and you can see here when we press down this push button, the digital controller may actually see a number of high inputs as opposed to just one. So this intermittent connection could be read as 5 separate input actions by a digital controller or programmable logic controller, and that would be bad. So let's take a look at what's inside. We can see here, there's the switch bounce, and there's the switch bounce again. And it's simply because we have springs in there. And what will happen is that that's going to cause more than one signal being registered. We see here on a scope, but the same thing would be registered on a digital controller. And so what we're trying to do is avoid that because, well, the spring bounce is going to be different for every different device. We can't really predict what it will be. As well as all of that current, and I know it's not a lot, but the current that's flowing through those contacts is going to corrode them and arc because we've got a whole bunch of arcing happening. And as we said before, the digital controller is going to register a whole bunch of inputs when really we just want one. So switch bounce is often known as ringing. And we want to remove that ringing because that can cause issues in our digital controller systems. So an SR latch with only one output used can help debounce or de-ring the signal sent from the spring-constructed pilot device. Now there will only be one signal received by the digital controller, which would be good. So if we push down the push button now, we can see that I have this combination push button that's connected one side to the reset and one side to the set. When I press it down, I'm going to see that my output goes high. However, the nature of this latching circuit will ensure that there is only one signal sent to the digital controller. So with debounce, it's simply going to be a solid on, and we're going to avoid all of this bouncing. And when I release the push button, it resets the system and we go off. So a clever use of an SR latch. Now, SR latches are typically sketched as their own individual symbol instead of a combination of individual logic gates. Usually it's a rectangle with an S, an R, and two Qs on the right-hand side. One is a Q and the other is Q bar. Now remember from Boolean expressions that a bar means to invert, and really that means the opposite. The Q bar will always be opposite of the Q. Now latches are for memory, they offer memory changes when the input signal changes. Flip-flops, the memory changes when the input signal changes and the clock signal allows for the change. Now what is a clock signal? That's a constant oscillating signal, a high and a low, that is used to control when signals are stored and reset in a digital logic system. Clock signals are sometimes also known as astable multivibrators. So here's an example. That is a clock signal. So this is something that is inherently built into digital logic controllers and programmable logic controllers and computers. Now there are three main types of flip-flops. There is the clocked SR, the D type, and the JK type. And you can see that each one has a connection for a clock signal. Although each flip-flop has two outputs, many times only one of them will be used, and it really is dependent on the situation. Remember, when the Q and the bar Q are opposite, the Q and the bar Q are opposites of one another. If one is high, the other is low. So let's take a look at a clocked SR flip-flop. In this system, the set signal will not be stored until the clock signal allows it. So what that means is that even though I may press that set button, it's not going to store it and make that light come on until the clock signal oscillates and allows for the AND gate to operate. Let's see how this works. So there we have my clock signal. It's a very slow clock signal for this example, so we can sort of see what's happening. Notice I just put it set high, and now when the clock signal went high, it is allowed to store that bit of memory. Now that bit is set, and when I go to press the reset, it will not reset it until the clock signal allows it. So let's watch that one more time. So I'm going to turn that off, and then go back up, press the set, and it will save the signal as soon as the clock signal goes high. And it doesn't matter if I leave that set high, it's not going to try to save another bit of data. And I'm going to go down there and I'm going to reset it. So an interesting application. Remember, the clock signal is what dictates when this system will save the bit. And that's sending it into memory. Now another type is called the D-type flip-flop. So a D-type flip-flop is a little bit different. And in this one, the set signal is only stored for one clock signal oscillation. Then it resets automatically. And so what you can see is there's a few other terminals here which we're not going to go into detail with, a pre and a clear. I just have those tied high to high values, so to constant power. I have a clock signal and I have the set. That's it. So let's see how this one works. So here we have the ultra slow clock signal. When I press the set, it will store that signal for one entire clock oscillation, and then it will automatically reset. So again, I'm going to go over and I'm going to press that set, and we'll see it store that signal for one entire clock oscillation. So there we go. It turns it on, it saves it, and now it's gone off, and when it comes back on, it turns it off. So it is all based on my clock signal. The clock signal is what determines what happens in this system. Finally, we have something called the JK type flip-flop. Now the signal can be set, the set signal can be stored according to the clock signal, and it can be toggled on and off if both the set and the reset are high at the same time. Again, we're not going to get into details as to why we would want to do this in different situations. We're just sort of looking at the basics here. So again, very similar to the D type, it's stored to the first one. The set signal is stored according to the clock signal. So let's see how this one operates. So there we have our really slow clock signal. And we can see here, I've set when the clock signal comes back on, it's going to be stored. There we go, awesome. And I have to press the reset, and the reset will then reset or extinguish or remove that bit from the memory when the clock signal goes high. There we go, makes sense. So it's really operating the same as the first logic gate flip-flop that we looked at, and that was the SR. Now, if I were to put both of those high, what we'll notice is that the output oscillates with the clock signal high and low. Interesting. And this is based on the arrangement connection of logic gates inside this JK flip-flop. So an interesting application. Again, if both the set and the reset are high, it oscillates. If instead I just have the reset on, well, then that means that the bit goes back to 0. So, interesting application. Now, the symbols beside the clock terminal of a flip-flop symbol indicate when the device will be triggered to store the signal. So, what I mean by that is that if we have just the clock like that, CLK, it means that it will trigger on a high clock signal, as in it would store the bit. If instead we have an inverting circle on the clock terminal, it means that this will only save a bit, this flip-flop, when the clock signal goes low. Now the next two are kind of interesting. They have to do with rising and trailing edge. So on this one, we can see here, the clock signal has a little triangle beside it. What this means is that the clock will only actuate or set the bit when it is on a rising or leading edge. When we're going from 0 to 1, that's when this flip-flop will store the bit. And finally, if I have an inversion circle and the triangle, it means that this will only save or transfer or store the bit into memory when we have a dropping clock. So, trailing edge, we have trigger on high clock, trigger on low clock, trigger on rising clock, and trigger on dropping clock. This means that at any point when the clock is high, if my set signal comes in any time here, my flip-flop will transition and set the bit. On this one, if my set signal comes in at any time while the clock is low, my flip-flop will set or save the bit. This one means it will only transfer or set the bit during this time period when it goes from 0 to 1. So, for example, if my set signal came in here, this flip-flop would not store the bit, only if my set signal was present during this time period. And finally, same with this one, the trailing edge. It will only save the bit, as in store the signal, during this transition from high to low. Now, flip-flops are used for a wide variety of applications in the digital logic world. By combining multiple flip-flops together, more complex tasks can be accomplished, such as memory storage, which is known as a register, and counters and timers. Let's look at memory storage first. Registers store bits of data. A bit of data is a single high or a low zero signal. There are two general categories of register systems because usually we are not just storing one individual bit, but we are storing a number of them. 4, 5, 6, 7, 8, who knows? Now those two different types are serial and parallel. In a serial system, my flip-flops are arranged so that the signals come in left to right, one bit at a time. Initially, the register contains only invalid data, or all zeros as shown here. Then, one bit at a time, because I have 4 bits here, I got 0, 1, 0, 1 that I want to store in my register. One at a time comes in, and what happens is it shifts from left to right in this situation, and all the way along until all of the bits are stored into the register. This is known as a shift register, and because we're shifting to the right, it's known as a shift right register. The other type of register we have in digital logic is a parallel register. Initially, the register is again empty, containing only non-data zeros. But instead of it shifting in left to right one bit at a time, all of the bits are shifted simultaneously into the register. So here's an example of a incoming shift register, and we're going to store the bits 1, 1, and 0, 0, and then they're going to parallel out into a storage register. And now we're going to change that bit data into 1, 0, 1, 0. So you can see here that there are different combinations of shift versus, serial versus parallel registers. It really depends on the application. And here's that final sequence. This one was serial in and parallel out. Let's look at a more complex one that actually has all of the individual logic gates. So we can see here is that we've got 4 bits that can be set, and I've got 4 logic gates. QB and DC are then connected here for QB at the top, and then I've got QC and DD, and these are then supplying QC at the top, and then QD coming out to QD at the top. Now what these are going to do, these are going to represent a shift register. And a shift register is going to bring one bit of data in at a time, and then it's going to shift it to the right. So this is dependent on clock pulses, and we're going to count the clock pulses. Right now we only have invalid zeros. On the first clock pulse, what we are going to do is we're going to store 1 on the first location, or the first bit set. All of the others shift over to the right. Now, as our clock pulses come in, we are going to record them in this table below. Now in my second clock pulse, I'm going to have that shift to the right. So now my 1 bit is now after flip-flop B. And so we're going to store those in the table below. And what you notice is that everything is shifting to the right. All of these digits are shifting to the right. So if we go to clock pulse or oscillation number 3, that 1 should get shifted over to the right-hand side of flip-flop A. There's 0 after flip-flop B, 1 after flip-flop C, and 0 after flip-flop D. So we're going to store those into our little table here. You can see everything's moving to the right by one shift. And finally, the last one to get that last bit of data in there, or bit of information or memory, is the 4th clock pulse. And now we've got all valid bits of data, 1, 1, 0, 1. On our 4th clock pulse, all of those are set in the register. So an excellent example of the sequence of operation that's necessary to shift from left to right in a serial register, and we can see the 4 individual clock pulses that are necessary in order for all of those bits to be set. Here's another example. This is a flip-flop timer, and what I'm going to do is I'm going to time something with flip-flops in binary coded decimal, or BCD. Each one of these light bulbs is going to go high and represent a 1 at a particular moment. Now, the clock signal rate will determine how quickly the system tracks time. The clock must then be set to accurately count seconds, and seconds will then be displayed, typo there, in binary coded decimal. So just as a review, binary coded decimal goes like this. For 0, I'd have all low, and for 1, I'd have 0001, for 2, 0010, 3, 0011, so on and so forth. So what I'm going to do is I'm going to shrink this table and provide it beside the system as it operates. All right, so there's my clock signal, and follow it along. Now I'm at 1. Now I'm at 2 seconds. Now I'm at 3 seconds. Now I'm at 4 seconds. 5 seconds. 6 seconds. 7. 8. And 9. Interesting, right? Now I'm going to reset it and go through the whole thing yet again. So we can track it and count binary coded decimal just by using flip-flops. And this is how timers function on a digital basis. They're actually counting, keeping track based on latches within flip-flops according to a clock signal. And that clock signal is what allows us to keep track of the time. The other one we can take a look at is almost identical, but this one's a flip-flop counter. I'm going to continue to use binary coded decimal, but I'm not going to use a clock signal. Instead, I'm going to use a push button. Each time the push button is pressed, a signal would then be sent to the flip-flops in the same way that a clock signal would. Each push button signal is then counted in the same way that we would have seen in the timer on the previous example. So the push button signal count is displayed in binary coded decimal. So let's again sort of follow through the process. So there's binary coded decimal. I'm going to come over, press the push button. There's 1. I've pressed it once. Now I've pressed it twice, 3 times. Notice that I'm just changing how long I'm holding the button down. Doesn't make any difference. Sometimes it's quick, sometimes it's long. And it will count how many times I've pressed that push button. There we go. I'm going to reset it. And there we go. Now I press the push button again, and it's going to keep counting all the way through. Pretty interesting when you can sort of see how digital systems actually track and keep count of time and numbers, counting and things like that in a really basic sequence. So that is how we use special combination logic gates for timers, registers, and counters.